probably know, red blood cells are in charge of delivering oxygen and other nutrients to the rest of the body and the brain. And it turns out that the structure that is in charge of carrying the oxygen, the hemoglobin, has different magnetic properties if it is loaded with oxygen compared to when it's not loaded with oxygen. So if a particular brain area is not very active, then it would need a bit of oxygen to, not to die, but it would not need too much of it. So the brain would make sure that it gets all the oxygen it needs, but not much more. Why waste, right? So overall, we would have this ratio between oxygenated blood and blood that is not oxygenated that would give us a certain magnetic signal. But as soon as a certain brain area becomes active, for example, the donut area in Homer when I presented a donut, then this brain area would need loads of fresh oxygen in order to maintain its activation. So this would mean that now the ratio of oxygenated blood would become higher, would be increased, which would give me a signal gain, a magnetic signal gain. This would cause the images of the brain to virtually light up wherever the oxygen consumption is increased. Okay? So now that we're all experts in physics of fMRI, we can move to my own research. So I've been interested in characterizing which areas in the human brain are responsible or dedicated to representing objects that are presented near to us within action space. So in my experiment, subjects are lying in the scanner, and they can see their body through this mirror. And what I do is present to them these balls that I bounce around in one of two targets, either near to their hand or further from their hand. And all I have to do now is find which areas in the brain respond most strongly to the ball when it is near the hand within action space, compared to the second position of the ball, which is far away and out of action space. So this is an image of the brain that I'm acquiring through the MRI. So you can see it from different positions. So this is if I look at it from here, horizontal view. This is a sagittal view, like that. This is a horizontal view. And all the bits that you can see here in yellow and red are areas that were more activated when the ball was approaching near the subject's hand compared to the same ball presented away from the hand. And you can see that lots of areas in the brain light up. So all these areas are much more interested or become more activated when the ball or any other object is presented near us and near our hands compared from away from the hand. So this is interesting, but it raises some questions. For example, what does it take for the brain to know that a ball is presented near the hand? Is it information from my muscles about where my hand is? Is it visual information of the hand? So to answer this, I repeated the same experimental design, but this time the subject's hand was retracted away from the near target. And instead of the hand, I placed a prosthesis, cosmetic one, by the near target. So now when the ball is approaching the near target, it's actually moving away from the subject's hand. But the subject can see this dummy hand that looks like his own hand, the same position. And I want to know if the brain is fooled by this dummy hand. So this is the image I've shown you before. So these are the brain areas that are more active when the ball is approaching the real hand of the subject. And I'm going to show to you now the areas that were interested in balls approaching the dummy hand. And this is what I get. So you can see that the brain pattern in these two experiments is remarkably similar. This means that all these brain areas were tricked into thinking that the ball is approaching the subject's real hand, even though there was no illusion. They knew that the hand is retracted. They saw me place things in the other hand and so on. So from this result, we can learn that visual information of the hand, even if it's illusory, even if it's not real, not reliable, would over-dominate our body representation. So is it any hand that we see that would make our brain explode with activation? To answer this, I repeated again the same experiment, but now I place the dummy hand by the far target. So when the ball is approaching the near target, It is moving away from both the real hand and the dummy hand. But when the ball is approaching the far target, it is actually approaching the dummy hand. And when I look at the differences in brain patterns between the near target and the far target, I find that when the dummy hand is far away from action space and away from the body, there's absolutely no activation. So all these brain areas that were really interested in the dummy hand was presented close to us, where our real hand could have been, are completely silent when the dummy hand is moved away. So this teaches us that in order for our brain to be interested, very interested in objects, then they have to be presented somewhere close to our body and by an image of the hand that could be interpreted as ours, at least according to the anatomical position. Okay? So this series of studies shows us that there are many brain areas that are interested in objects that are presented next to us, and particularly next to our hands. And this led me to ask, what would happen to the brain of people that have lost their hands, and therefore can no longer present information about objects next to it? So, if I would lose my right hand, I think the immediate consequence would be that my action space would shrink, because prior to the amputation, all of this would be my action space. But if I lose my right hand, then my action space is now confined to the left side of the space and to the center. And I thought that maybe this shrinkage of action space, this asymmetry induced in action space, may generate some changes in visual perception. So to test this hypothesis, I raised a group of amputees, unilateral amputees, so they're only missing one hand. And I gave them this very, very basic visual test. So they were asked to sit in front of this screen. So this is outside of the MRI scanner. It's just like in a room, like this room. And I give them this cross here, this red cross, that shows them where the center of the screen is. And then I would flash to them briefly these two targets, to the left and to the right of the center of the screen. And all they have to do is decide which of these two targets is further away from the center. So it's completely visual, it has nothing to do with amputation or anything else. So just to give you a flavor of the task, before I go, I want to say that they were sitting very close to the screen, at 50 centimeters distance, so the targets are well within reach inside the action space. So just to show you how it feels like, this is, let's say this is the center of the screen that you're looking at. And these two targets will be presented for a short period. And you have to decide which of these two targets is further from the fixation. So in this particular case, I would say that the right target is further. Okay? But this is going to be a lot more difficult because the targets are not going to stay there for a long while. You ready? Which one was further?
Right.
Right, okay. And now?
Left.
Okay, let's make it really difficult. Yeah, I think left. So as you can see, it can become very, very difficult. And we can actually reduce the time that they can see the targets to make it very difficult. What I find is that our left-hand amputees, that is amputees that have lost their left hand, tend to report that the target that is presented to the right side is further away compared to the target that is in the right. So they actually tend to underestimate the distance to the left side, which is the amputated